Alright, so now we're going to go ahead and talk about the chain rule. So we talked a lot about stuff like derivatives of sums, differences, products and quotients, and things like that. So the chain rule gives you a formula to find the derivative of a composition of functions. So remember from pre-calculus, function composition is when you have one function inside of another one. So like here we have f of g of x. Okay, so g of x is inside of the function f. So that's a function composition. The chain rule says the derivative of that is f primed of g of x times g primed of x. Okay, so in other words, you can think of f as the big guy because it's on the outside, and think of g as the little guy because it's on the inside. So the chain rule says the derivative of f with respect to, the derivative of f of g of x with respect to x is equal to the derivative of the big guy evaluated at the little guy times the derivative of the little guy. Okay, so that's pretty much what the chain rule says. It's kind of strange if you've never seen it before at all, but we'll do a lot of examples with this in the next few videos. Before we prove this real quick, let's go ahead and see some other notation here. Another way to express this is df dx equals df dg times dg dx. Okay. So the derivative of f with respect to x is the derivative of f with respect to g times the derivative of g with respect to x. So that's another way of kind of thinking about the chain rule here. This notation here is a little more intuitive. It's nice, but you want to be careful because you can't just say, oh, alright, I'm going to cancel this dg and this dg, then I'm just left with df and dx. You can't really do that, and the reason is that df, dg, and dx they don't represent real numbers. They're what are called infinitesimals, so you can't really treat them like real numbers. But that's kind of a topic for a later discussion. So for now, let's not worry about that. But I just want to show you this other notation here, because it will come up in your studies every now and then. And it is more intuitive than this. But if you're doing actual calculations or things like that, in general, this kind of notation up here is more useful. Okay, so let's go ahead and see where this comes from then. We're just going to use the alternate definition of a derivative, and we're going to have to do something kind of strange here, but we'll explain it all. So let's just go ahead and jump in. So d dx of f of g of x equals the limits as t approaches x. Okay, because we're doing the alternate definition here. Limit as t approaches x of... So we're going to have f of g of t, actually, f of g of t, right, minus f of g of x now, all over t minus x. Okay, so now comes the strange part. So what we do next, it's really not going to be very clear what we're doing or why, but as we go further on in the proof, it'll be clear why we had to do what we're about to do. But anyway, let's not get too far ahead of ourselves. So what we want to do next is define a new function, and we're going to call it, let's come up here, and define a new function, big F of y. Alright, and it's going to be a piecewise function, okay, so it has two pieces, and the first piece is going to be little f of y minus little f of g of x, all over y minus g of x. And it's defined to be this if y does not equal g of x. Alright, we're going to have room over there. Let's back up a bit. If y does not equal g of x. Okay. So that's the first piece of the function. And the second piece of the function is just going to be f primed of g of x if y does equal g of x. Okay. Alright, so what we're actually going to show, so why do we have this function here? What's so useful about it? Well, we're going to see why. And also, what's this lowercase y here? What is that? Well, it's just a variable that we use to define this function. That's all it is. It's nothing more, it's nothing less, there's nothing special about it. We have to use y because we're already using x over here. Okay, here we have an x for something else, and we're already using t in the limit. Okay, so we're just going to use y here. We could just easily use z or w or s or whatever instead of y, but let's just use y. Doesn't really matter. Anyway, so what we're going to show now is that, so that's our next step, is now we want to show that big F of y, okay, this is what we want to show. We're going to show this. Big F of y times g of t minus g of x all over t minus x equals this guy over here. F of g of t minus f of g of x all over t minus x. Okay, actually, I'm sorry, this shouldn't be a y in here, this should be g of t. Sorry, so actually what we're going to show is that big F of little g of t times g of t minus g of x over t minus x equals f of g of t minus f of g of x over t minus x, which is this guy right here. All right, so here's our function big F of y. So we're going to apply the function big F to little g of t. All right, and we're going to show that no matter which piece we're on, this expression always equals this. All right, and then we're going to use that in the proof. So anyway, let's go ahead and show that. So there are two pieces here to worry about. So let's just look at one piece at a time. So let's look at the first piece. So here, f of y, we're doing big F of g of t. Okay, so instead of y, we're going to have a g of t now. Okay, basically we're just going to plug in g of t for y. That's all we're doing. So let's say we're on the first piece. So let's say if g of t does not equal g of x, all right, then what happens? Then big F of g of t times g of t minus g of x over t minus x equals what? Well, big F of g of t, so big F is a piecewise function, right? So let's come up here. Which piece are we on? We're on the first piece because we're assuming that our input, which in this case is g of t, we're assuming that it's not equal to g of x. Therefore, we're on this first piece. Okay. So the function big F is defined in terms of y, but now we're going to plug in little g of t instead of just y. All right. So it's just like, if we have a function f of x equals x squared, and if we plug in 2 for x, we want to find f of 2. It's the exact same idea. Here's f of y equals a big old mess here, and what we want to do is find f of g of t. Okay, it's the exact same idea. Just plug in g of t for y. And we know we're on this piece because we're assuming that g of t does not equal g of x. All right? So because we're on the first piece, we're going to take this part over here. So what we have is little f of g of t minus little f of g of x all over g of t minus g of x. All right? That's what this function is defined to be under this assumption. Okay, so it's little f of g of t minus little f of g of x all over g of t minus g of x. All right, and then times, this stuff is still here, g of t minus g of x all over t minus x. Okay, so now what happens? Well, now this over g of t minus g of x times g of t minus g of x over that. So g of t minus g of x, they cancel, right? And how do we know that's okay? Well, first of all, why wouldn't it be okay? Well, it wouldn't be okay if this were ever 0, because then we'd be dividing by 0, right? And that'd be bad. But we know that won't happen because we're assuming g of t is not equal to g of x. Therefore, g of t minus g of x is never equal to 0, and it's okay to do this. So then we see that all we're left with is kind of running out of room here. So let's actually come down here. So all we're really left with is f of g of t minus f of g of x all over t minus x, okay? And that's actually what we wanted to show. Okay, we want to show that this guy is always equal to this, all right? And that's our result here. So we've done that now for the first piece, okay, but now we have to do it for the second piece, right? So we want to make sure that this function big F of little g of t times that always equals this, no matter which piece we're on. And we've just shown it for the first piece. Okay, so now let's show it for the second piece. All right. I know you're probably wondering what this all has to do with the proof of the chain rule, but we'll explain that when we get there too. So now let's assume we're on the second piece. Okay, so if little g of t does equal little g of x, then we're going to be on the second piece of the function here. So then what we have, this stuff up here, then little f of g of t times g of t minus g of x over t minus x equals what? Well, little f of g of t equals, or sorry, big F of g of t equals little f prime of g of x, okay, because here now our y, remember y is little g of t, okay, that's our input to the function, and we're assuming that it equals g of x, therefore we're on the second piece now, okay, so this is going to be little f primed of g of x times, now here, what's happening here, if g of t equals g of x, then g of t minus g of x is 0, right, so 0 over t minus x, but actually this is just some number times 0 divided by some other number, okay, so this whole thing is just 0, alright, but actually, okay, that's not quite what we want, right? Why is it not quite what we want? Because what we want is actually to show this. We want to show that f of g of t times this whole mess equals that whole mess, right? But we're not quite there, but actually we pretty much are there. Why are we there? Because we're assuming g of t equals g of x, okay? Therefore, f of g of t equals f of g of x. Therefore, f of g of t minus f of g of x is 0. So this actually does equal f of g of t minus f of g of x. Okay. So this is 0, okay, because we're assuming g of t equals g of x, so that automatically means that f of g of t equals f of g of x. All right. And now if we divide this all by t minus x, we still have the same thing. Okay, because this is just 0 divided by some number, all right, which gives us 0. All right, we know t minus x is not 0 because we're taking a limit as t approaches x, so that means t is always different from x. Okay, t never equals x. So t minus x itself is not 0, and that's good. All right, so just to recap real quick, big F of little g of t times g of t minus g of x over t minus x. We're assuming g of t equals g of x, therefore we're on the second piece over here. All right, so we have little f prime of g of x, all right, times 0 over t minus x, because g of t equals g of x. And that just equals 0. But that's the same thing as f of g of t minus f of g of x, all right, because g of t equals g of x, therefore f of g of t equals f of g of x, therefore f of g of t minus f of g of x is 0, all right? So what we've just shown is that no matter which piece we're on, okay, no matter which piece of this function we're on, we always have that big F of little g of t times g of t minus g of x over t minus x equals this mess here, which is actually the same thing as this, all right? So now we've just shown that. Okay, so in other words, we have just shown that this right here, we've just shown that that equals this. All right, so this thing right here and this thing over here, those are equal. Therefore, their limits are equal. Okay, so let's go back to purple now. So then this is going to equal the limit as t approaches x of f of g of t times g of t minus g of x, all divided by t minus x. Okay? So that's so remember, what we've just shown in the past few minutes is that this expression here equals this expression here, no matter which piece of the function big F we're on. That's what we've just shown. Therefore, the limit as t goes to x of this has to equal the limit as t goes to x of this. Okay? So continuing, what we actually really have here is limit of a product. Okay, so square brackets not really necessary, but it's good to have them just to be clear on what's happening. So limit of this times this, we know that that equals the limits of the first thing times the limit of the second thing, as long as both of these limits that we're writing down now exist. All right, and they do. That's not something we have to worry about for here. Okay. By the way, if you're wondering why we have to go through this process of defining this new function big F, I'll explain that later on in the video. But for now, let's go ahead and keep going with this. So here, limit as t goes to x of big F of little g of t. Now this is a piecewise function, right? Big F is a piecewise function. So when we take a limit as t goes to x, there's two pieces here to worry about. Okay, but hold that thought just for now. And then let's go ahead and look at this piece over here, or this factor, this part. Limit as t goes to x of g of t minus g of x over t minus x. What is that? That's just the derivative of g, right? That's just g prime of x, right? So whatever's happening over here, this is just going to be g prime of x. All right. Okay, that's good. So now we want to know what exactly is this. All right. Well, we're going to come back up here to our function definition. So let's get a new color, and then we'll section this off. So big F of y is this. So that means that f of g of t equals this. Big F of little g of t equals little f of little g of t minus little f of g of x over g of t minus g of x if g of t does not equal g of x, right? And it equals f primed of g of x if g of t does equal g of x. Okay, so what we actually want to look at is what's the limit as t goes to x of this thing here. Okay, that's what we want. We want the limit as t approaches x of big F of g of t. All right, so let's look at each of these pieces here and see what happens. All right, if we take a limit, let's look at the second piece first because it's actually easier. If we take a limit as t approaches x of the second piece, what's happening? Well, it's a limit as t approaches x. It's a limit as t approaches x of f prime of g of x. All right. And what is that? Well, there's no t in here, right? This is just f prime of g of x. That's all it is. There's nothing about t. Okay, so this limit here depends on t, but this expression doesn't have a t in it anywhere. So as far as this limit is concerned, this expression is actually just a constant. Okay, it's not really a constant because there's an x, but the limit only cares about t. Okay, in other words, the variable for the limit is t. All right, but this doesn't have any t in it, so the limit just thinks this is a constant, basically. So this is actually just f prime of g of x. All right, so that's the second piece there. The second piece was easier to deal with, that's why we did it first. But now let's go ahead and look at the first piece. Okay, so for the first piece, if we take a limit as t goes to x of the first piece, what do we have? Let's zoom out just a little bit. We're going to have limit as t goes to x of f of g of t minus f of g of x, all divided by g of t minus g of x. All right. And now notice this looks pretty similar to this, right? Limit as t goes to x of g of t minus g of x over t minus x equals g prime of x, right? Because here's t, here's x, here's t, here's x. Therefore, g prime of x. All right. Here is g of t, g of x, g of t, g of x. All right. Therefore, this limit is going to be f primed of g of x. But also, the reason that we can say this, this is okay because on this piece, g of t is never equal to g of x. All right. What happens if g of t is equal to g of x? Well, then somewhere along the way we're dividing by 0, and that's bad. We can't have that, right? So that's a really, really subtle technical detail to worry about, but it's very important to point it out, and it's really easy to overlook it, and it's really bad to overlook it also. But so we want to make sure that we cover that, and that's actually why we went through this process with this function big F, so that we can handle this technical detail here. Because you can sort of give a general idea for what this proof will be without the function big F, but then you run into this problem here, and then you're not really handling it correctly. But this is how we take care of that with that function big F. So anyway, just to recap real quick, here, limit as t approaches x of g of t minus g of x over t minus x. That's okay because as t approaches x, t is always different from x, right? T comes into x from the left or from the right, so t and x are never the same thing. But the problem here as t approaches x, g of t and g of x might be the same thing. We have no idea. You know, they could be the same, they could be different. We have no idea what g is really doing. But because we define this function big F, and because we're on this first piece tells us, okay, g of t and g of x are not the same thing. Therefore, this limit is okay to take. And from definition of the derivative, this limit just equals that. All right. So really subtle detail there. And again, just real quick, the difference is that limit as t approaches x, on the bottom, t minus x, that's okay, because t and x are never equal to each other. But here, limit as t approaches x, on the bottom, g of t and g of x, they might be equal to each other. T and x aren't, okay, but g of t and g of x might be equal to each other. And that's a problem that's taken care of with this function big F here. So that's why we need the function big F. All right, but anyway, what we've just shown is that the limit as t approaches x of big F of little g of t always equals this, all right, no matter which piece we're on. And that's good, because now we can just come back over here and say that, okay, no matter which piece we're on, we're always going to have the same thing, and this is going to equal f primed of g of x. Okay, and that's our formula for the derivative. F prime of g of x times g prime of x, or in other words, derivative of the big guy evaluated at the little guy times the derivative of the little guy. Okay, and that's pretty much where this formula comes from for the derivative of a composition function here. And that's the proof of the chain rule there.